good morning students. So we have successfully completed the first unit. So let us start the second unit, distributions here. So before going to the distributions, just once again we will just revise the first unit. So in first unit we have seen what is probability, then how the probability of the event happens, then how we have to assign the constant value to the event of a random experiment, that is random variable. And as we know that the random variable is classified into the discrete and continuous random variables. Then if we assign some function to the discrete and continuous random variables, then it is a probability mass function and a probability density function. But just simply if you calculate the expectation of the random variables here, it is not enough for us, right? We have to calculate the mean of the random experiment also, right? So mean of the random variable is different and mean of the experiment is different here. So for that they have introduced the distributions. So just like the random variables, here distributions are also classified into two types as discrete distributions and continuous distributions. So just we have a glance on the contents in this unit, that is binomial distribution, Poisson distribution, normal distribution, gamma distribution and variable distribution. So the first topic is here binomial distribution. So what is this binomial distribution? So in the word itself we have bi, that means two variables here. That means experiment wherever it has fixed outcomes. So there we can apply this binomial distribution, right? So if you can see here, this is the just graph of the binomial distribution, right? So let us consider the example on this. The basic example we consider for probability is here tossing a coin. Since tossing a coin has only two fixed outcomes here, head and tail. So if we consider head as the probability of success and tail as the probability of failure, then what is the probability of success if a coin is tossed for some multiple number of times, that means for 5 times or 6 times or 10 times here. Not only the tossing a coin, we can consider the data transmission from the cell phone through the cell tower here, right? So if in the data transmission, if we find that there is a 6% error in the data here, then what is the probability of reducing that error to some 3%? There we can use this binomial distribution here. And not only in that, of course we can calculate this binomial distribution for the quality of a product. So as we know that the quality of a product is nothing but defective or non-defective, right? So what is the probability of defective products and what is the probability of non-defective products? What is the average of the defective products and what is the average of non-defective products, that we can obtain using binomial distribution. Apart from this, you can consider the present situation, that is the COVID, right? So here the entire world is just running back to introduce a new drug for this COVID, right? But after introducing the drug here, again we have to implement on some 10 to 15 people whether the drug is here curing the disease or it is not curing the disease here. That means if you introduce any drug here, again it has two outcomes, that is curing the disease and not curing the disease. So there also we can apply the binomial distribution. So here, knowingly or unknowingly in our daily life, we are just using this binomial distribution. So if we come to the probability mass function of binomial distribution, it is nck into p power k into q power n minus k, right? But here I have given it as 1 minus p. Why? Because here if p represents the probability of success, then q represents the probability of failure, right? And always the probability of success plus probability of failure is equal to 1. So that's why here q can be written as 1 minus p. So here x represents the discrete random variable which is always a 0, 1, 2, so on n. So it is only for fixed number of trials here, just like the mathematical definition of probability, right? But again when the number of trials are large in number, then it automatically tends to the next distribution, that is Poisson distribution, right? Then n stands for the number of trials, p is the probability of success and q is the probability of failure here. Then by applying the expectations or by using moment generating function, we can find the mean of the binomial distribution, that is mean is np, number of trials, into probability of success, and variance is here npq, that is number of trials into probability of success into probability of failure. So by using this mean and variance of the distribution, we can just interpret about the random experiment here. So let us see some problem also, right? Suppose here a biased coin comes up heads with a probability 0.3. So here no need to calculate the probability of success. It will be given in the problem directly. When tossed, what is the probability of achieving 0, 1, 2, 3, 4, 5, 6 heads after 6 tosses. That means here the coin is tossed for 6 times. So n equal to 6, right? And it is given 30%. So p equal to 0.3. Then q is nothing but 1 minus p, that is 1 minus 0.3 is 0.7. Then we have to calculate the probability of achieving 0 heads, 1 head, 2 heads, 3 heads, 4 heads, 5 heads and 6 heads here. So probability of x equal to 0, probability of x equal to 1, x equal to 3, so on till 6 we have to calculate. So here probability of x equal to 1, it is 6c1 into 0.3 power 1 into 0.7 power 6 minus 1, which is equal to 0.3025. Then probability of exactly 2 heads is 0.3241. Probability of 3 heads is 0.1852. Probability of 4 heads is 0.0595. Probability of 5 heads is 0.0102. And probability of 6 heads is 0.0007. So using calculation operations, clearly you can obtain these values very easily here. Then consider the second problem also. Here in a restaurant, 70% of people order for Chinese food and 30% for Italian food. A group of 3 persons enter the restaurant. Find the probability of at least 2 of them ordering for Italian food. So first go through the problem and just identify the number of outcomes. So what are the outcomes here? 2 types of events, Italian food and Chinese food. So the probability of Chinese food ordering is given as 70%, that means 0.7, and the probability of ordering Chinese food is given as 30%. Italian food is given as 30%, that is 0.3. So how many people visiting the restaurant here? 3 people. So for those 3 people, we have to find the probability that at least 2 of them ordering for Italian food here, right? So we have considered the Italian food as Q here, that is 0.3. So at least 2 means exactly 2 or more than 2 also they can order. So probability of x greater than or equal to 2 we have to find. So probability of x greater than or equal to 2 is given by probability of x equal to 2 plus probability of x equal to 3. So probability of x equal to 2, if you substitute in the probability mass function, it is 3c2, 0.3 power 2 and 0.7 power 3 minus 2, which is 0.7 power 1. It is 0.189. And for probability of x equal to 3, it is 3c3, 0.3 power 3 and 0.7 power 3 minus 3 is 0.7 power 0, which is equal to 1. The value is here 0.081, right? So the total probability that at least 2 persons ordering Italian food is 0.27 here. So like this we can calculate the mean and variance and the probabilities of binomial distribution. Some more problems are there, so those problems we will discuss in the next class.